Can I see? The camera just turned itself off. Okay. So people seem to like carrots. So let's say that 25% of the vegetables you eat are carrots, and then, 25% of the time I get carrots in my veggie box, and then let's say 7% of the time I get turnips, and 1% of the time I get celeriac, that's why I didn't recognize it. 2% of the time I get kohlrabi, and now I have to make sure this adds up to 50% of the time I get potatoes. So I'm keeping track of 32, 33, 35, 40, 50, wait, no. That's not sure. 40, 90, that's 100. Potatoes, tomatoes, so this is 95 and 0.05. Okay. Let's suppose it was this. What we're trying to do is come up with a tree such that if we give carrot weight 0.25 and turnip 0.07, actually I haven't received a turnip yet, and this is 0.01, then what are we trying to do? We're trying to come up with a tree, a binary tree that has minimum expected depth. Okay? This should sound very familiar. It's the same problem. This is not even a reduction, one of those reductions I love so much where you take a problem and turn it into another problem. This is the same problem. Okay? So you already solved it. Alan is only 70 years late. Otherwise, he would now be a famous computer scientist for proposing merging the two smallest lists. Okay? It's not that bad. I mean, one of the things, people have this, I was actually warned by one of the other professors, people have this mental block that this course has a well-deserved reputation for being really hard, and so people do not sometimes they do not try an obvious thing, which we are expecting people to try. Now, admittedly, I started with this practice one because with the unequal lists, I think it's a bit more natural to merge the two smallest lists. In this case, taking the two smallest probabilities and taking the two, you start out with a collection with a forest of trees, each of which consists of a single node. And what you do, you take the two nodes with the smallest weight and make them the children of a node whose weight is now the sum of their two weights. That's not as natural, and that's probably why it took Huffman, so that there's this story that he went through pads of paper the night before the exam trying to come up with a solution. I mean, that's why he probably did. If he'd been thinking about it as merging lists, maybe he would have got it right away. Actually, it wouldn't have been an open question to get out of an exam in MIT. But it's 70 years later, and I hope this is an easier way for you to understand it. Okay. And I probably have I have 7 minutes. And did I just shut my browser down? Okay, in 7 minutes, so we've seen Huffman's algorithm in disguise. Now we've seen Huffman's algorithm in its normal form. So now I want to talk about the complexity of Huffman's algorithm. So how do you actually implement this thing? Well, now, who said, are we doing this with rotations? Now we think about data structures. Everybody now knows and loves Huffman's algorithm, and I can safely put it on exams and things, right? Okay, well, I know at least one person is never forgetting Huffman's algorithm. Okay, so I have 7 minutes. I'll check my email afterwards. If you've been sending me messages, please have patience. I'll get back to you. So, how would you actually do this? Well, how would you do this? I have to keep track of time. Okay, so I have 6 minutes. So, how people teach this, the implementation of this, is usually with cues. Right? So what you do is you, so for example, you could do this as a heap, okay? You learn heaps, you love heaps, I think. So what you do, but think of it just as a priority queue. So you take all the probabilities as weights, and you put them in a min heap, right? So this is some like data structure blob thing, and it just gives you insert and extract min. And you now say, okay, give me the minimum, and it gives you the smallest weight. And now you say, give me the minimum, it gives you the next smallest weight. And now you take these two things, you put them together, you sum them, and now you insert it back into the heap. Okay? So how, with the min heap, depends how you implement these things, but if you implement a min priority queue that has extract min, so with a heap, I think extract min takes, with the implementations you've seen, extract min and insert both take take logarithmic time, right? I should have reviewed this. So at least one of them takes logarithmic time because you can't sort in less than n log n time in general. So that's going to take you, if you do it with a heap, it's going to take you order n log n time. Now, that's usually, so I can send you notes, I've written notes out for classes I've taught before, where it diagrams, and it is a valid question to ask on an exam. Please, here are a set of probabilities, build me a Huffman tree, and you have to like take them and merge them, blah, 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 blah. Okay. There is a cool thing which I can maybe teach you in 3 minutes, which is Van Leeuwenhoek's algorithm, which if the weights are sorted already, somebody gives you the probabilities sorted, then Van Leeuwenhoek's algorithm runs in linear time, which is kind of cool. So what you do, you start out with 2 queues. Oh, I shouldn't have erased these probabilities. Phew. Does anybody remember what they were? From the smallest, it was 0.01 and 0.02 and 0.05 and 0.07 and 0.1 and some other stuff. Does anybody remember? No? Okay, whatever. This is probably enough. So this is one of these 2. Actually, this doesn't even have to be a queue because I'm never going to use it again. And then I have another one which is initially empty. What you do, each step of this algorithm, I'm going to look at my 2 queues. This is a bit like merging the 2 lists. I'm going to take, and I'm going to look and say, okay, which one has the smaller? And then I'm going to take the smallest thing off. So in this case, this is empty, so I can't take anything off. So I'm going to take this off, and so in one hand I'm holding 0.01. And then this is still empty. So I'm holding 0.01. I look at them again, and I get the smallest thing. This is again here. Okay, now I add them together, and I put them in this queue. So 0.01 plus 0.02 is 0.03. And now I can look and say, okay, this one is smaller, so I take this one, and this list is empty again. And now this one is smaller, so I add them up, and this goes away, and this is 0.08. 0.03 plus 0.05. Now this one is smaller, so I take it off. So what you do is you keep taking these, you have these two sorted lists, priority queue. Well, this one it doesn't matter, right? You have these sort of two lists, and you take the two smallest things off from either the head here or the head here. You add them, and then you insert them at the back of this second list. Always insert at the back of the second list. So maybe eventually when this one goes empty, then you ignore it from then on, and you take the smallest thing here, and then the next smallest thing, and you add them together and you put it at the back. Okay? Why? So, and you always put it at the back. So the trick to Van Leuven's algorithm, and I'm now run out of time, is that you can say, why does this keep the things sorted? Well, whenever I'm going to insert something here, right? So in general, I have these two lists.